Day 14. Extended polymerization. Oh, it's a polymers problem. He likes his polymers problems as well. These usually are like, what are they called? Like regular expressions? No, not quite. Automata? Yeah, it usually delves into the area of automata, which is a very interesting theoretical computer science field, and it's one of the first things you learn before you learn what a programming language is and why it even works. So it's important stuff, but it's a lot of theory that you eventually forget, and it's tends to be something you never address again because, you know, now that you've established programming languages exist, they work. You don't tend to need to go back to this theory, but it's interesting stuff. I mean, the reason we care is because we want to know that a computer can interpret a program in one and only one way. If it can't, then it's a failed language. You can't have ambiguous languages. So the automata theory sort of comes along with theoretical results which prove that under certain conditions there can be only one way to interpret a section of code. And that is what is known as context-free grammar. Alright, well, the incredible pressures at this depth are starting to put a strain on your submarine. The submarine has polymerization. I wonder if there's actually quite an intersection between the chemistry side of polymerization and coding. Probably. Equipment that will produce suitable materials to reinforce the submarine, and the nearby volcanically active caves should even have the necessary input elements in sufficient quantities. The submarine manual contains instructions for finding the optimal polymer formula. Specifically, it offers a polymer template and a list of pair insertion rules. Okay, so it's 2 characters to 1 character. A rule like AB to C means that when elements A and B are immediately adjacent, element C should be inserted between them. These insertions all happen simultaneously. So starting with the polymer template NNCB, the first step simultaneously considers all 3 pairs. The first pair NN matches the rule N to C. So element C is inserted between the first N and the second N, okay. The second pair NC to B, so B is put there, and then H is put there. But it happens simultaneously, which is maybe the tricky bit. So you can't do them one at a time, because then you mess up the indices. Like, if you were to... Well, it wouldn't really mess anything up. But you gotta make sure you're not looking... Like, if you put a C in there, you can't then do NC. Because that's from a previous step. So yes, you have to like just make a list of all the insertions you need to make before you make them, and then do them. Okay. Fine. Thinking a bit ahead here. Note that these pairs overlap. Yep. Polymer grows quickly. 7 blah 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 blah. So after step 5 it has length 97. After step 10 it has length that. After step B occurs that many times, C occurs that many times, H occurs that many times, and N occurs that many times. Okay. After 10 steps, interesting. I wonder what part 2 is going to be. Is it going to be something crazy big and we have to be really smart? You can't really break it up into fragments because the borders, the gaps between the fragments that's a pair, so it's not an independent problem. So you can't really break it into independent sub-problems. But then if you find pairs that don't belong to this list, then they would technically be... No, they wouldn't. Yeah, so if you had... Like, if you found a... I mean, do we have every possibility here? We've got CH, HC, BH, HH, NN, CC. It looks like we have every possibility. In that case, that idea goes out the window. Anyway, if we do it 10 times, I think it'll be... interesting. All right, so... Okay. Okay, so... So polymer... So they have the template. Okay, so template equals f.readline dot strip, and then just fetch the empty line, and then from whatever's left, we've basically got this. So we've got what do they call it? Pair insertion rules. Okay, we'll just call it rules. Wait, how did they do it? So, saying yeah, all right, so I think first we just want to decide what we're inserting and where. So every pair should exist as a possibility, right? Should they? How many have we got? 2. We've got 100 rules. That doesn't sound like it's a complete set. Like it would be a power of... No, it wouldn't be a power of 2. It would be the number of letters. Choose 2. So do we have... I mean, either way, we could write it. Alright, so we need to find what so let's call it expand. So okay, so we've got a new. Okay, so first we just have to decide what the insertions are and where, and put them in a list. Okay, so let's just make a list of pairs. It's going to be like the index and what to insert. So for -1 because the last item doesn't have a following character. So pair equals s be I to I plus 2. Yeah, and then if pair, we'll check if it's in the rules. Then we are saying we have to insert. So the index we insert in is I plus 1. But this isn't... Hang on. This index isn't... So either we keep track of an offset or we start from the end of the list and work backwards. But that wouldn't work either. I think we'll use an offset. So we needed a... If we've inserted a character, then everything is going to be offset. So it starts with 0. So it's going to be I plus 1 plus offset. And because we've inserted a character, that means from now on, wherever we look, well, this is confusing as heck. Couldn't you just make all the pairs, then insert, then recombine? Um, I'm not sure what you mean, but I mean, there's different ways that we could do that, but I could just create a essentially, yeah, I think. Hang on. Okay, don't worry about this offset. We say new. Just call it temp. So yeah, so we've got, let's say, so we're looking at fs, and we know we have to insert something in between. So on the list, we'll put f. We'll put the thing that goes in between. And nothing else. And then we move on to sk. And then we do that. We'll put in the s. We'll put the thing that goes in between, and the k. Yeah. Then there's no issue there. Yeah, we don't need to deal with this. So I am range. So for each pair, we just put the first of the pair and the middle, but not the end. And if we do that, should be fine. And then of course we have to add the last character. So for I am range length pair. So we always put that character in, the first of the pair, and then we check if that pair is a rule, and if it is, then we put in yeah, this is a clean way to do it. So we just do that, and then at the end of it, put the last character, and then we return this all joined up. Yeah, I was overcomplicating it. I mean, like, break it into the FKKS, whatever, then add the extra letter, and recombine them so you don't have to worry about offsets for the insertion. Yeah, I guess that's what I'm doing at this point. So each stage of this loop is looking at first FK, then KS. Yeah, that makes more sense than worrying about offset. And the offset didn't even work anyway, because it would differ between the characters we keep and the characters we insert. All right, so that is an expansion. Let's try it out. In range 10. S, so it'll be so we do it 10 times. Let's see how big this gets. Okay, not too bad. All right, so So what did they want us to find? Most common element and subtract the quantity of the least common element. So it's just look at these counts and do the max minus min. In fact, I think counter even has a function built into it to do that. Like you want the range or something. Most common. Well, that'll tell us what the element is. We don't care what the element is. Total. Maybe not. I don't know. But this is just max minus min. Two, 3, 6, 0. Correct. 40 steps. Oh dear. Oh dear. Yeah, there's no way we are storing this string in memory. Okay. Well, okay, so we have to break it into. So the interesting thing here is that like if we had just fs by itself and sk by itself, if we just did those like 10 times each, that would still end with the s, and that would still begin with the s, so they would overlap. So you would, if you worked out those problems independently, worked out what the resultant string was, then that's breaking it into subproblems, isn't it? And you just, that one s is duplicated, so you take that off. So really, it's just it's really just a case of solving the problem for fs, sk, vv, vo, oops, and so on separately, and then to get the final totals, you just have to subtract 1 for each of these in the middle letters. So the problem reduces to like being able to find the count for one pair. Now that's still going to be too big, but like it means once we know the answer to one pair, like if it comes up again, we already know the answer. We already know the count for it. But okay, let's think. We're doing it 40 times, so we can make some sort of recursive function. Time to turn the laptop into a space heater, maybe. Um, So really, we want to just know how many pairs. So instead of this counter that I've done, I've counted how many times a single individual letter appears here. We actually care about how many times each pair appears. So like in this initial one, FS appears once, SK appears once, and for the most part, it doesn't matter what order we do things. Like if we found PP separately and KBN separately, we could add them all together. The only thing that matters is that C is at the end and F is at the beginning, which means they get counted once only. But everything else gets counted twice because it's always part of two strings. So if we knew, how do we make this rigorous? So given a string, we only need to know three things about that string: starting character, the end character, and the full count of all the pairs in there and how many there are. We don't need to know anything else. We don't need to know what order they come in because it doesn't matter really. Like if I were to swap FP, and we could test this out. Like, well, no, because we would actually change things. We would actually change the pairs count. But if let's work under that assumption. So all right. I think I can sort of see how we'd write this. So we want a method that, given a string, we perform one step. So we need to know the start, the end, just the start character, the end character, and basically a dictionary of pairs and their counts. And what we'll return is the new pairs counts after a step is performed. Yeah. think this works. And we can test it on this example. So if we know that it starts with a certain letter and ends in a certain letter, and basically a full count of all the pairs, that means the pairs list is just as big as 100, right? And each of these will have a count, an integer. So we'll return a pairs list of size 100. So it's just every step is only using like returning something of size 100. Nothing's actually growing except the values of the ints are growing, but that's fine. So yeah, okay. So we want a new pairs equals, let's say it's a fresh counter. So for pair count in pairs.values, so we've got so somewhere in this string we've got this pair. So if that pair is in the rules list, if pair in rules, then every instance of those pairs splits into whatever the rule gives us. So the left side will be pair 0 plus rules pair. The right side will be pair be rules pair plus pair 1. So the new pairs left will increase by that same count. It's 1 for 1. And if it isn't, I don't know if this happens, but if it isn't in the rules, then that pair just stays intact. So you just say new pairs of the original pair plus equal count. So, and that's almost everything. So now we've basically added up all the pairs. So now we've wait, did the start and end characters actually matter here? No, they only matter at the very end when we're trying to yeah, they don't matter in this function. The start and the end will always be the same. All right. So that return, and then we return this new pairs list. Okay. So we've got this template. So we know what the start is. Start equals template 0. End equals template minus 1. So what we want is pairs equals counter. Is there a quick way to count the? We'll just do it like this: for I in range, length, template minus 1, pairs I to I plus 2, so that's each of the pairs. Uh, oh, no. Count 1 for that. So now we've got our initial pairs. Then for that in range 40, pairs is replaced by step pairs. So finally, we know what the counts of all the remaining pairs, and now we want to just separate that into letters. So every letter is going to get double counted except the start and end. That's the point of knowing the start and end. It probably won't matter. Um, hang on. Yeah, no, that's right. Okay, so letter count is a new counter. Counters are great, they just make things easier. Um, for pair count in pairs. So each of the individual letters just gets added in. Okay. But everything's been double counted. And now so just to be absolutely correct, we have to hang on. And still confused about what to do with the start and the end. Okay, so basically we've double counted every letter in the middle, but we've correctly counted the one letter at the start and the one letter at the end. All right. Yeah, because there was no pair preceding the first letter and there was no pair after the last letter. So I think the easiest way to resolve this is just letter count, the start character, just take that out. So it's going to be probably an odd number. Because everything was double counted, but the first character is counted once because there was one pair which had it, but there was no pair before which had it. So this is an odd number. Take that out. Take this one out as well. Right? And now we halve everything in the counter. So for pair in pairs, this gets rid of all the double counting. Those should be even numbers. And now we put back in the start and the end. I don't know if a cleaner way to do this. Like the numbers might be so big that this extra start and end doesn't matter, but this is, oh no, it will matter because they're asking us for the exact quantities. Well, of the most common element and least common element, but it could be F or it could be F or C. We'll find out. And then we just have to do this. But that has to be done 40 times. We didn't. Oh no, we did. Yeah, so that's there. Just separate this out. All right, we'll try it. That's the wrong word there. String index out of range. Pair count in pairs.items. Let me check I've got the right pairs here. For some reason I've got a single character in here. I think I've done the indices wrong. What? It's not supposed to be like that. For age pairs template. That should be I+2. So SKV over, yeah, so it's one of each. Two of these. Okay, good. That number? I mean, there's so many things that could have gone slightly wrong here, but I think the gist of it is correct. No, it's too high. All right, now we have to figure out. Um, um, I mean, we should test it on our example here because this process will work. We don't have to do the step process anymore. Let's encompass this all as a method. Define get final counts for a given template and a given number of steps. And here we basically do all of this. That gets us the final count. Part 2 counter equals okay. So in theory, we could use this for part 1. So if we do 10, that's what they asked for. 2360 is what we got before. 4720. It's exactly double. Why have I got exactly double? So we halved the numbers there. Oh, well, no, this is the wrong counter. We're counting, we're halving them. We didn't halve them, basically. But can I not just do this? Am I allowed to do this? Yeah. Yes. Okay. So 40. So it's half. Oh, sorry, I didn't have the IDE visible. So basically what happened was this line was wrong. I was halving the pair counts instead of the letter counts. So we have basically exactly half of what we had before. Correct. That was an interesting problem then. And if we go back to the code, we can now just use that process for part 1. We don't have to we don't need an expand method because that's inefficient. Just say it's just this, isn't it? Just expand. Yeah, we don't do this anymore. Yeah, there we go. So it really came down to knowing that order doesn't matter. Like, you have a pair somewhere in the string, it will end up as 2 pairs. And it doesn't matter where they are because everything happens, insertions happen inside a pair. So it becomes basically a series of fully independent problems, with one exception. The first character and the last character might be slightly off, but I mean, let's actually print final counter. Like we probably got lucky, and the F and the So this is the final count. So like F 1619. So the start character F and the last character C. So C was not the biggest and F was not the smallest. So it didn't matter. Literally just knocking one character off, but it's completely but if F or C were the most or least, then it would matter because we'd be off by one in this answer. Unless both F and C. Unless one was the biggest and one was the smallest, then they'd cancel out. That'd be a bit funny, but yeah, it's mostly just if you have this many of this pairs, then next turn you'll have this many of this pairs, and every pair splits into two pairs. That's cool. Yeah, that's a good problem. All right. Um, can go for one last one. On to 15. Well, yeah, we'll go for it. Hopefully it doesn't take too long.